So Pluto is sort of in the periphery of my research, but I wanted to bring this topic to you because this year is Pluto Eve. 2014 is the year before the encounter. This is a long-lived mission already. I'm going to put up this timeline just to give you an illustration of what I mean by, and I might have mentioned this on the radio, this is not a new mission because it's already been in space. It's been taking great data already for several years. This mission was launched in 2006, and it was the fastest spacecraft, to Jupiter. It took a direct shot at Jupiter where it received a gravitational assist so that it could cut 3 years off of its travel time to Pluto. I'm very much interested in Jupiter science. This is a great opportunity to add yet another spacecraft to our Jupiter database. So I'm gonna show you a little bit about that as part of this ongoing mission. So this was 2007 already that we had an encounter with Jupiter. And since then, it's on an 8-year cruise phase to Pluto, where most of the time this spacecraft is asleep. It's hibernating. Every now and then we wake it up. Every week we ping it to make certain it's still there, but every now and then we wake it up to take data. There's actually a rich data set that this space mission is accruing in the void between Jupiter and Pluto. It's taking measurements of what we call the solar wind. At the end of this year, at the end of November, this mission becomes active. It is no longer going to be hibernating. It will be turned on. It has a powerful telescope on board with an optical camera. So it will begin imaging of Pluto. So this Pluto encounter starts this November. So I think this is a good time to introduce you to this mission so that you can keep track of it and be aware of some of the exciting discoveries that are coming up. Closest approach occurs in 2015, summer of 2015. What's out there? The solar system really consists of 3 zones. There's the rocky planets that we're familiar with. We're one of those, the Earth. So Earth, Venus, Mercury, and Mars are rocky. There's the gas giant planets, Jupiter, Saturn, Uranus, and Neptune. And then there are the ice dwarves. There's a lot of material out there. Pluto is not alone. It's in a belt of material, call it debris, call it what you will, called the Kuiper Belt. And so when you think about all of the mass in the solar system, there are more ice dwarves than there are rocky planets. Yet no spacecraft has been sent to this region. So this is really a pioneering mission that I'm really looking forward to. So what are these ice dwarves? It's this debris pile out there, and it's thought that these are really ancient relics from the early formation of the solar system. These are, if you will, the building blocks from which the planets that we're familiar with were built. So this schematic gives you kind of an idea of what we're talking about here. Here's Jupiter and Saturn. Here's the Sun, Jupiter, Saturn, Uranus, and Neptune. And Neptune really lies, it's the inner region of this Kuiper Belt. Pluto is in an orbit, in a highly elliptical orbit like this. Sometimes it actually comes inside of Neptune's orbit. And it's one of many, many objects out here. It's not alone. There are other Plutoids, if you will. So these are what are called Trans-Neptunian objects. In 2006, the discovery of Eris, I believe, this is a planet that looks larger than Pluto. This sparked a controversy. If Pluto is not alone, and there are many other Plutoids out there, do we really want to call it a planet? And so there was a debate, and it was decided that it would be designated as a dwarf planet. I talked to the PI of this mission, the New Horizons mission, Alan Stern from Boulder, Colorado, and he said, let's continue that debate once we have images of this thing. I guarantee you that when we actually see this thing, a round sphere which orbits the sun, everybody will be back on board that indeed Pluto is a planet. So those of you who are concerned, rest assured, the PI firmly believes that this is a planet. But the exciting thing is that there's more like it out there. So the Kuiper Belt is also the source of cometary impactors. Sometimes these chunks, these icy chunks, make their way into the inner solar system. And it's known to be heavily endowed with organic molecules. which are really the raw materials for life. So this is what makes Pluto special, what makes it interesting. Okay, so a little bit of history now. When was Pluto discovered? This was done by a guy named Tomberg in 1930 at the Lowell Observatory in Arizona. He spent many nights looking through telescopes, and during the days he compared images. So he'd look at these star maps and try and find motion relative to the stars. So let me show you this. This would be an example of what he was doing. He'd look at an area in the sky and look for something that might be moving relative to the star background. And that's how the discovery of Pluto was made, just by persistent observations and scouring and comparing images. And that was the discovery of Pluto. It's a faint object. It's difficult to see. You can see how relatively faint it is with respect to the stars, background stars in the sky. Pluto has a moon named Charon. Those of you who know your Greek mythology probably know that these are all names that have something to do with the underworld. Okay, Charon is a big moon. Here's just to give you some reference, some scale here of how big Pluto is and how big Charon is. Charon's a big moon. You can almost think of this as a binary system. These two sort of tend to orbit around each other. But Pluto's the more massive, and you can see how large it is relative to the lower 48 here. It has 5 moons altogether. Other moons were discovered recently, 2005, Nix, Hydra, I've forgotten. Think of all of the figures in the underworld from your Greek mythology, and you've got it. There are 5 of them altogether. If you look at Pluto and Charon from the Hubble Space Telescope, that's an Earth-orbiting telescope that gives us very high resolution, this is what you might see. It's kind of a fuzzy blob. Here's Pluto, here's Charon. So this was an image that was taken from the Subaru telescope in Hawaii on Mauna Kea. So if we look now at Pluto, this would be a raw image of Pluto as seen by the Hubble Space Telescope. It's pretty blurry, it's pretty fuzzy. We've seen some spectacular images from the Hubble Space Telescope, but this is a small object, it's faint, and so we're not going to see it very well. There's another moon out there called Triton. This one orbits Neptune. Also sort of fuzzy. That's the best Hubble Space Telescope resolution. If we were to take the moon and give it a comparable resolution, that's what the moon would look like. So there's not a whole lot to learn when that's the best you can see. So again, here are these sort of fuzzy Hubble Space Telescope images, and this is a fixed-up version, if you will. The Hubble's best images there, and then these smoothed, modeled images might look like this. So in fact, Pluto sort of has a blotchy character. The surface is dark in some places and white, light in other places. So we don't really know what's on the surface. We think that there are ices, there are frosts, but really it's not clear what we have here. So now, to put New Horizons into perspective, it's got a telescope on it with a camera. And prior to about 150 days to closest approach, the resolution of that camera will exceed Hubble. So that's why everything turns on in November of this year. The images will start to flow. We'll start to image this moon, this planet, sorry, and its moon, Charon, and the science fun begins. This is a surface map of Pluto based on Hubble Space Telescope again. And again, envision this thing. It's dark in some regions, white. What is this white? What's the dark? Perhaps the best clue we have of what Pluto might look like was from the Voyager mission. If some of you are familiar with Voyager, you know these spacecraft are still flying. They were launched a long time ago, 30 years ago or more. I don't remember when they were launched. Long time ago, but those missions flew past. This one, Voyager 2, went past Neptune and got these very high resolution images of Triton. So it's thought actually that Triton may be a close cousin of Pluto. And so we have these images to sort of start to think about what we're seeing, what causes the blotchiness on the surface. Is it topology? Are there some craters? Are there smooth areas of frost? What exactly is there? It's always fun to look at artists' rendering, an artistic rendering of what the surface of one of these objects looks like. This is Triton with Neptune in the background. I put these things up because I really think that it's important for you to wonder and imagine what these places look like. And again, once we get these images back from the New Horizons mission, we'll have a good idea. So again, there's speculation. What is Pluto? What is Charon? What are they made of? And this is the best guess right now. It's thought that the middle of this planet is really made of rock, and then the outer layer is made of water ice. So it's sort of an icy rock mixture. Maybe Charon is completely mixed like this rather than differentiated. It's not clear. But this New Horizons mission is going to settle this. For the science that I do, this was an incredibly important observation that was made in 1988 and perhaps really motivated this New Horizons mission. And that is, if you look at a planet like Pluto and you wait for a star to essentially pass behind the planet. So here's an observer on Earth looking at Pluto. A star passes behind, and what you do is you look at the starlight, the intensity of the starlight while that transition occurs. And if you see that instead of just a sudden dropout in intensity, you see this more gradual decline in the intensity, that means that there's actually an atmosphere there. Pluto has an atmosphere. And this really precipitated tremendous interest in this planet. So I call this the Great Escape. Atmospheric physicists started to contemplate this. With spectroscopy, they could determine what the atmosphere was made of. It's actually made of things like methane, N2, CO, all these nasty things. Nevertheless, models were put together, and it was suggested because this planet is small, it has weak gravity, and this atmosphere can actually escape. So I call this the Great Escape. The Pluto's atmosphere may be escaping into space, sort of like the way a comet gas escapes from the comet itself. So what this suggested now is if you have this escaping atmosphere, this is a unique situation that we have in the solar system. And atmospheric scientists have suggested that Earth's early atmosphere, while Earth was forming, had an atmosphere that also was escaping like this. So in terms of comparative science, this is a great opportunity. If you can understand Pluto's atmosphere, maybe you can better understand Earth's early primordial atmosphere. Okay, so the New Horizons mission is really to find out what is Pluto really like. We have these remotely sensed diagnostics. We have the star occultation. We have these fuzzy Hubble Space Telescope images, but now it's time to go and really learn. Let's go and explore this planet. So following that atmospheric observation, so starting in 1989 through 2003, there was a real effort to get a mission to Pluto. And that ultimately became the New Horizons mission led by P.I. Alan Stern. So what makes this special is the New Horizons mission is the first NASA mission to a new object in the solar system in over 30 years. So the Voyagers were the last ones to go to Neptune and to Uranus and Saturn and Jupiter. So this captures the essence of this special mission. So there was an urgency to get this mission going. The proposals went out in 2001, and I believe the selection was made shortly thereafter. But if I show you Pluto's orbit, you can see why this is important and why we act quickly. This is Pluto's orbit, and this is a timeline. So here's the sun. Pluto's closest to the sun in 1989. This is called perihelion. So back at the end of the US Civil War, it was farthest from the sun. Lowell was born in 1885. He was the founder of the Lowell Observatory, where Pluto was discovered by Tombaugh in 1930. Here's the launch of Sputnik. Here's the Apollo moon landing. Here's the discovery of the moon Charon. Here's the New Horizons launch. And here's Pluto in 2015. So there was a real motivation. While Pluto is close, let's get it launched. While we can use a Jupiter gravity assist, let's get it launched. And so this mission was put together with a fairly sense of urgency. Okay, so what's on this spacecraft? Some of this may not be that interesting to many of you, but I like the names. So if nothing else, enjoy these names. These are the instruments. Here's the spacecraft. It's sort of a triangular shaped thing. It's got some propulsion systems. It's got an antenna, and then it's got all these things hanging off of it with different names like Ralph, Alice, Lori, Rex, Pepsi, Swap. So the Rex instrument uses radio communications. So looking at beams from Earth to this antenna, you can diagnose Pluto's atmosphere. Using the high-resolution black and white images from the Lori telescope, you can look in high-resolution, great detail at the surface. This is just an example of what you might see. With the Ralph instrument, it's a wide-angle color camera that looks at both visible and infrared, so we can look at surface temperatures of Pluto. With the Alice instrument, we can look at the composition and structure of Pluto's atmosphere. This is a spectrograph, an ultraviolet spectrograph. With the SWAP instrument, we can measure the solar wind interaction with Pluto's escaping atmosphere. And this is really the science that I became involved in. So just a quick reminder here. Remember, the sun is this gas ball, and it's got a wind that's blowing off of it. These are charged particles which flow away from the sun and go out through the solar system. This wind interacts with Pluto's atmosphere and generates a perturbation. And so some of these instruments, like the SWAP instrument, that stands for the solar wind at Pluto, is going to measure this interaction. There's another instrument called Pepsi that's also a particle detector, which is also going to look at escaping ionized gases from the atmosphere. This mission also has, I think this is one of the unique aspects. I always love to see student participation. This is flying a dust detector. Who would have ever have thought of making a dust detector? I have a dust detector at my house. It's called a vacuum cleaner. Dust exists in the solar system. It's actually a very important diagnostic. For Jupiter, for example, a lot of dust comes from Jupiter. This was built, it was designed and tested by students at the University of Colorado. So this is strictly a student-driven detector that's making important measurements all the way through the solar system. Okay, so I like Jupiter. It's convenient that this spacecraft went to Jupiter. Jupiter has this really, really neat moon. And if anybody here thinks our moon is cool, let me tell you, this is a really cool moon. This moon is chock full of volcanoes. There are volcanoes all over its surface. In fact, if you look carefully in this image, you can see a little glow. Here's Io, and there's a volcanic plume erupting on the North Pole. This is data, believe it or not, from the New Horizons mission. This is, I believe, the Lori camera. And it captured this fantastic event. This is the Svastar volcano erupting up on the North Pole of the moon. You can see that it makes this sort of fountain. This is a couple of images stitched together to give you a sense of how it's flowing and moving. This shows you some of those hot spots on the moon. Here's some of those plumes coming from the volcanoes, but these may be perhaps like lava fields. It's hard for me to imagine or to describe to you what it might look like. Let me show you a picture of Io taken from the Galileo spacecraft. This was a spacecraft that orbited Jupiter for nearly 10 years during the decade of the 90s. Looks like a pizza, yes? Okay, each one of these is a little caldera event. Any of you who have been to Hawaii might like to envision walking across a lava field and seeing that as a representation of what you might find on this surface. There are hot spots. It's very active, a very active moon. Here's an artistic rendering of what Io might look like with these toxic fumes of sulfur dioxide coming out of these volcanic vents. So let me just give a little interlude before we continue with the New Horizons mission. And let me describe to you the journey that I took as a graduate student at the University of Alaska Fairbanks studying the Earth's aurora. How on earth did I end up studying Jupiter? So let me just give you a flavor of this. Some of the work that I did as a graduate student involved research at Poker Flat, doing rocket experiments. Some of these experiments, this is a very early experiment that I was not involved with, but The technique was basically to detonate a cloud of gas somewhere in the Earth's atmosphere or ionosphere or in near Earth space environment. And these gases glow when they're illuminated by the sun. So you can imagine these experiments essentially was akin to taking a magnetic field from a magnet and sprinkling iron filings on it. So now we can trace the magnetic field and we can look at where it goes. Some of the work that I did in my thesis involved some of these active experiments that were done from a satellite called CRESS. And these are clouds of barium that were detonated over the Caribbean. So we're looking at, if I should show you these in color, I would, but if I could show you this, this would be green and this would be purple. So these make nice emissions that glow, so they're interesting to look at, and it tells us something about how gas interacts with magnetic fields. So we proposed an experiment when I was a student, and that was, could we make one of these clouds of gas somewhere up in the Earth's atmosphere or ionosphere or space environment and cause an interaction to happen that would generate an auroral emission? So that was a neat idea. And then I was introduced to this moon Io at Jupiter. So this is another artistic rendering of what Jupiter's space environment looks like. And what you see here is this moon, which is magnetically coupled to the planet. And then there's this gas cloud, this ring of gas, which we call the torus. Where does this gas come from? It comes from all of the volcanoes. So these volcanoes spew gas into the space environment around Jupiter and makes what we call the Io plasma torus. So what's really cool about this is if you look at this, this is a synthetic image, but see this spot up here? This is Jupiter's aurora. And here's a spot. If I were to go to where Io is located and trace along the magnetic field lines, well, by golly, that spot actually maps right to where Io is. The moon is making an aurora on Jupiter. It's doing it all the time. There's an electrodynamic interaction. So I discovered, why do we need to do artificial experiments at Earth when, in fact, this is a naturally occurring experiment which happens all the time? So for me, this was an opportunity to explore auroral physics. I add this slide just to joke around a little bit. I love giving talks about the aurora in Fairbanks because I know all of you know what I'm talking about. If I go and do this in Boulder, Colorado, about a third, maybe a quarter of the audience will know what the aurora is. And so for the young people in the audience, I always have to add something like this just to remind you. So thank goodness, whomever this, was this Walt Disney? I don't remember. This is Brother Bear. You see the aurora in lots of these animations, which is great. But I always tell people, you haven't seen the aurora till you've stood on the ground, looked straight up, and there it is. You can't go be in Minnesota and see it glowing on the horizon. That doesn't count. You gotta come up here. So, has anybody here not seen the aurora? Dare I ask that question? If you haven't seen the aurora, please come and see me afterwards. Okay, we'll fix that. Okay, so Jupiter actually has 3 types of aurora. I actually refer to this as plural auroras. Earth has 1 type of aurora in comparison to Jupiter. So Jupiter has these aurora that are associated with moons. There's Io, Ganymede, Europa. They all have these auroral spots. Then there's this main steady oval of emissions, and then there's this weird stuff that swirls around in the poles that we don't actually really understand. We think that it's caused by the solar wind interaction. We don't know for certain. These are images from the Hubble Space Telescope of Jupiter's aurora. So you can see occasionally, you'll see the Io spot there. You'll see these swirling emissions in the pole, and then you'll see the sort of this steady auroral oval. The driving mechanisms at Jupiter are completely different from the aurora at Earth. And so from my perspective as an auroral physicist, I really cherish the idea of being able to study the system and do comparative studies. How is Jupiter's aurora similar? What are the similar characteristics? And so that's the field of what I call comparative auroral physics or comparative magnetospheres. Okay, back to New Horizons. So here we are. This is an animation of the spacecraft flying down a strange structure which shows up in these colors. So what on earth is all this about? What you're seeing here is you can see the moons, the Galilean satellites orbiting Jupiter, and then what's being painted on here is Jupiter's magnetic field. Jupiter's magnetic field makes a cavity in space called a magnetosphere. The New Horizons mission made a completely unique observation of one of these structures. It flew directly down what's called the magnetotail. No other spacecraft has ever done this. So for the field of magnetospheric physics, which is related to auroral physics, this is a great opportunity, a fantastic opportunity to explore and understand. So although this is a Pluto mission, it connects back to magnetospheres and to the Aurora very much. So most of the missions to Jupiter orbited. These are the Galileo orbits in here. The Pioneer missions came in and flew out. The Voyagers came in and flew out. Cassini mission that went to Saturn just glanced past this structure, and the Ulysses mission came in and went out. This yellow line here, this is the New Horizons mission, and again, this terra incognita, this is an unexplored territory for magnetospheric physics. The data that we got back surprised everybody. We had an expectation of what we would measure. We expected something that was predictable, that was uniform, that was structured in a very predictable sense. And instead what we found and I'm not going to explain this data to you, just enjoy the pretty colors, but these are energy spectrograms, and what you see is a blobby structure to it. So you see a lot of reds, that means high count rates, counting a lot of particles, followed by voids here. And so if we were to picture the structure of the magnetotail, so it's sort of like the wake behind the rock in the river. There's a wake behind it, there's a void in there, and what we're finding are these puzzling blobs. It's not the layered and ordered structure that we expected. And so I'm not going to say much more about this, but this is a very hot topic right now in the field. It's generating a lot of enthusiasm. We've had conferences where we're looking at this. It is not fully conclusive what we're looking at. It's an ongoing process. Very rich and data set from Jupiter. When you don't really know what you're looking at, sometimes it's convenient to look at numerical models. So we use lots of nasty equations in space plasma physics and auroral physics, and we feed those into a computer, and the computer does the calculations for us and generates what we call simulations. So we can model what these funny magnetic structures look like, and so working with the data and working with models, we come up with these types of pictures. So I often call this the Star Trek model of the magnetosphere. It's thought that maybe it has some spiky wings that stick out on the flanks like that. So this is ongoing science thanks to the New Horizons mission. Okay, so here we are leaving Jupiter. This was, remember, 2007 was this flyby. It lasted for couple of months or so as it flew through the system. Occasionally, we wake the spacecraft up, test the instruments. So these are actually the first images of Pluto and Charon returned from the New Horizons spacecraft. Obviously, they're fuzzy still. They don't even compete with the Hubble Space Telescope, right? But it's a milestone, a benchmark for the system, for this mission, right? Where is New Horizons now? You can go onto a website if you're curious, and you can look. I copied this from a couple of days ago, so this isn't quite accurate. It's not quite up to date, but it's close enough. Here's Earth, Jupiter, Uranus, Neptune, and here's New Horizons right now. So it's come from Earth, past Jupiter, straight out towards Pluto. So it's almost to the orbit of Neptune, not quite, but it's getting there. Here it is in another view. Here you can see this sort of slanted orbit of Pluto. So it's only got that much farther to go. So what's out there? It's just space. Like I said, for about 50 days of each year, this spacecraft is woken up and it takes data. So it has this swap and Pepsi instrument. What all they do is they stare into this solar wind which is flowing out, and it counts particles. It just counts 1, 2, 3, 4, 5, right? But it also knows how fast the particles are going. And so this is actually an interesting measurement because, again, we don't have much spacecraft data that far out in the solar system. So this is just to illustrate that we have this new data. The analysis is ongoing. I want to point out, I don't want to go into the details, but there are 2 peaks here. One of those are protons, the other one is helium. And this is characteristic of the solar wind. But I want to show you this shoulder here. It stretches down here and has a small peak here. These are particles that originated in interstellar space. So not from the sun. And what we're seeing is we're seeing more and more of them as we go out in the solar system. And so this is actually a very interesting measurement. It's showing us what the composition, what's the nature of the interstellar medium. So not only are we looking at what we call the solar wind, what's in between the sun and Pluto, but now we're actually making measurements of gases that originated out who knows where. It's just interstellar material. So what do I do with Pluto? I actually do numerical simulations. I'm one of those guys who take all of my equations, I stuff them into a computer, and I turn a handle. It's not that trivial. But I'm able to simulate interactions. These are called electromagnetic interactions. It's all of the equations that I use are the same equations that I would use to describe how the aurora works. And so what I'm doing is I'm looking at how the solar wind medium interacts with Pluto's escaping atmosphere. So you may think, well, so what? If you're trying to really understand Pluto's atmosphere, why do you care about how the solar wind interacts with it? The problem is if you have a puffed up atmosphere that's really, really thin, it's really hard to see it. And what we want to know is we really want to know what the details are of this extended atmosphere. It's very extended, very puffed up. It turns out that, to make a long story short, that interaction has a very pronounced effect for the SWAP and PEPSI instruments. So the interaction of the solar wind is actually supersonic. So we know what happens when an aircraft is flying faster than the speed of sound. If anybody's heard a sonic boom, it's unmistakable. So obstacles to the solar wind flow are also supersonic, and you get what's called a bow shock. Think of the wave that you get in front of a boat or something. When the solar wind passes through that structure, which you can kind of see here in gray, it has a very pronounced effect in the way that the SWAP and PEPSI instruments measure particles. And that is now an indirect measurement of Pluto's atmosphere. If we understand that interaction, we can understand the atmosphere. So what I'm doing is really it's numerical simulation of a complicated interaction which ultimately gets back to the science of Pluto's atmosphere. These are some more pictures from these simulations. Again, I talked about this wave, so you can imagine the obstacle is this blobby thing. Pluto is, you wouldn't be able to see Pluto on that plot. It's just a tiny, tiny dot. But this is the gas which streams off, and you get this bow wave in front of it. And you can see how there's some interesting structures that show up in these simulations. Okay, so what happens then? This encounter occurs, so we turn on our telescope at the end of this year. We encounter Pluto in the summer of 2015. The plan is to reorient this spacecraft. There's other Kuiper Belt objects out there. And so, time permitting, funding permitting, this spacecraft will be directed to a new Kuiper Belt object, and presumably I think the intention is to rendezvous sometime in 2016 or 2017. So this mission is not over after Pluto. So keep your ear to the ground to find out where it's going next. For those of you youngsters in the audience, I encourage you, look up, ask questions, explore. And with that, I will end and take any questions that you may have. Thank you.